All right, I think we're about ready to get started. Alice, if you're ready.
Sure.
Okay. So I would like to welcome all of the attendees that have joined us. Today is our March Distinguished Lecture Program, where we've been grateful for Alice Bowman's time to join us for this webinar today. I think there's a lot of us who will be very much interested in her talk about the New Horizons program with her work at Johns Hopkins Applied Physics Lab. The way I'd like this webinar to go is all the attendees, you're currently muted, just so that we can keep the background noise down. But please feel free to submit your questions to the Q&A link that's down at the bottom of your page. And at the conclusion of the presentation, I'd like to get through as many of those questions that we can. So without further ado, our distinguished lecturer for this evening.
Okay, hi everybody. Thank you very much for inviting me to speak. I always love to talk about Pluto and the spacecraft, New Horizons. Let me just share sound. Okay. My background, I have a Bachelor of Arts degree in Chemistry and Physics from the University of Virginia. And I've worked out in California for Aerojet, and then I worked for a small software company also out in California. Then I worked in Denver on a classified spacecraft for the Air Force. And then I came to the laboratory in about 1993, and I've worked on a number of space missions there. So I've been there ever since. So that's a little bit about me. New Horizons is the name of our spacecraft, and it is obviously funded by NASA. Mission to Pluto is a primary mission, and then extended mission to the Kuiper Belt. And the spacecraft is now almost 50 AU from Earth. So just to recap, this is stuff you probably learned when you were in elementary school. This is a sort of a big picture view of our solar system. And 1 astronomical unit, AU, that's what I'm going to use in referencing to distance. So 1 AU is the average distance between the sun and the Earth, and it takes a photon from the sun 8 minutes to travel 1 AU. The reason why I'm pointing that out is because we communicate with our spacecraft basically at the speed of light. And so that gives you an idea of how long commands or telemetry will take to either go from Earth to the spacecraft or from the spacecraft to Earth, depending on where it is. When I was growing up, Pluto was a planet. We had 9. And beyond Pluto, there wasn't much that I was taught. In the early 1990s, Jewett and Liu, both out of MIT, found a way to detect these objects, Kuiper Belt objects that had been theorized in the 1950s. And they started detecting them. And once they figured it out, there were hundreds that were discovered. And so beyond Pluto, the mission of this spacecraft was to encounter a Kuiper Belt object. And in January 1st, 2019, we did a close flyby of Arrokoth, which is also known as 2014 MU69. And during the encounter, we had nicknamed it Ultima Thule. So all of those names really represent the same object. So this is the best picture we had of Pluto before New Horizons. This was taken with the Hubble Space Telescope, still our most powerful telescope. It's in Earth orbit. And if you're a scientist, you would look at this picture and say, Pluto is going to be really interesting when we get to take pictures of it up close. And the reason they would say that is because there's a lot of contrast in this picture. So there was features that they knew were on the surface that we just couldn't see. Now, if you're an engineer, you might say, well, it might be interesting, but I'm not so sure. So anyway, that's really the reason why, one of the very, I guess, the public reason why we wanted to go and visit Pluto and see what it was like, what kind of mysteries it had. Also, the scientists have been doing something called an occultation with a star, with Pluto, and had determined that there was likely an atmosphere on Pluto. And so also one of the things we wanted to study was that atmosphere. And I'll talk a little bit about occultations a little bit later on. The red line is the path that our spacecraft took to get to Pluto. And you can see that the white ellipses are the orbits that are represented by the 8 classical planets. And then we have Pluto's orbit that's represented by that yellow oval. And you can see that Pluto is kind of tipped on the ecliptic. So the ecliptic plane is the plane that our classical planets lie in. And then you can see Pluto is kind of tipped. And so right at the get-go in 1930, when Claude Tombaugh discovered Pluto, we knew it was kind of an oddball because it had this kind of strange orbit. And then the green lines point to those milestones that the spacecraft took. So we launched January 19th, 2006. We had a Jupiter closest approach, gravity assist, February 28th, 2007. And even at that, with the gravity assist really shortening our transit time by about 3 years, still it took us 9.5 years to make a close approach of the Pluto system, and that was July 14th, 2015. And then we flew another 3.5 years to encounter Arrokoth, which is 1 billion miles beyond Pluto. Pluto is 3 billion miles from Earth, or 32 AU. Some of the challenges that we had, obviously the distance, Pluto 32 AU, Arrokoth 44 AU. And when you think of this in terms of light time delay, at Pluto, it means that it took a little less than 4.5 hours for our commands to get from Earth to Pluto. And at Arrokoth, a little more than 6 hours to go from Earth to Arrokoth. Obviously it took a lot of time to travel, even though this spacecraft holds the record for the fastest man-made object to leave Earth at 36,000 miles per hour. Even at that, it took us 9.5 years to get to Pluto and 2.5 more to reach Arrokoth. And because of this distance and this really the light time delay, we needed a spacecraft that could really take care of itself, because by the time we see something that might be a problem on the spacecraft, the information is already a one-way light time old. So in the case with the spacecraft at Pluto, 4.5 hours old. So we had to have a very robust autonomy system on that spacecraft that could save the spacecraft during the time it took us to get a command up to the spacecraft to fix whatever was wrong. Power, this is a nuclear powered spacecraft powered by RTG, a radioisotope thermoelectric generator. We have one on board the spacecraft. I say that because as a comparison, the Voyager missions each had 3. And so what this means is that we had limited power. We had about 240 watts of power when we launched, and when we got to Pluto, about 201 watts of power. So we had to plan that encounter and the switching on and off of instruments very carefully. And just like all NASA first reconnaissance or first visits, you only get one chance to get this right. You can't turn around and go back. You're not an orbiter, so you can't try to get information on the next orbit. So the spacecraft is about the size of a baby grand piano. That white dish there is the high gain antenna. It's about It's 2.1 meter in diameter, or about 7 feet. The weight is a little bit more than 1,000 pounds. This part right here is the cooling fins of the RTG. So this is the heat's generated, and what we call waste heat, or the weight that we aren't shunting inside the spacecraft, will get dissipated by these fans on the outside. And then we have 8 payloads or instruments, I'm sorry, 7 instruments or payloads. Particle instruments, these are the SWAP, PEPSI, and SDC, which is a student dust counter. And then imagers and spectrometers, Lori, Alice, and Ralph. And then a radio science experiment called REX. So what do we do? Obviously, well, I don't know about obviously, but I work on the engineering side. So we are the operations group, and I'm the manager of the group of people that keep that spacecraft healthy and safe. We develop the spacecraft schedule of events. So we work with the scientists and with the engineers. We might be doing calibrations or checkouts of redundant systems, etc. So we develop those commands that accomplish those objectives. And we configure the ground station to talk to the spacecraft. And we bring that data to Earth. And if there's anything that goes wrong in the spacecraft, we are the team that leads that effort to fix those problems. So we use the Deep Space Network, or DSN, to communicate with our spacecraft. There are 3 complexes around the world. They have a 70-meter antenna, which is about 230 feet in diameter, and a number of 34-meter antennas, which are about 112 feet in diameter. 3 complexes, again, around the world. So as the Earth rotates, you can contact your spacecraft using one of these complexes. They're spaced about 120 degrees apart. So as the video is showing, you have Madrid, Spain, Canberra, Australia, and then Goldstone, California. So just to give you an example, and again, this is exaggerated. Time and distances aren't to scale. But here, this is a representation of a ground antenna, so at one of the complexes. And then we have our spacecraft that is going to be communicating with Earth. And in this example, I'm using the spacecraft when it's at Pluto. So we send up commands in about 2-week chunks of time. And we have a set of memory on board the spacecraft. We virtually divide that in half. So we have one set of commands for this 2-week period that goes to half of the memory. And then once that memory is starting to be used, then we will load the second half of memory with the next set of commands, the 2-week period that's going to happen. So what that means is that when we get to the end of this command set that's on board the spacecraft, there's a seamless transition into the second set. And then once that happens, then this first set becomes free. And so we just do that. So here we've loaded commands to the onboard memory, and there is an onboard clock that counts down, and each command is tagged with a time. And once it reaches the time where it says send telemetry, it starts sending telemetry down, and then the spacecraft makes its way across the sky, but that telemetry is still coming down to the ground antenna to be received. And then finally, a one-way light time later, or in this example, 4 hours and 25 minutes, you see that you finally get that first set of telemetry that was sent. But look how far that spacecraft has moved across the sky. So likewise, if you want to send commands to the spacecraft, then you're going to take a ground antenna, you're going to point it to where the spacecraft's going to be a one-way light time later, and you can see that spacecraft's moving across the sky as viewed from Earth. And then finally, a one-way light time later, the commands are received on the spacecraft. So I mentioned that we usually load the spacecraft memory with 2 weeks worth of commands. The set of flyby commands is particularly dense, and that's because a lot of scientific observations are going on. This is the best time to conduct those. And we decided on a 9-day period, and there's a number of reasons for that. It had to do with recovery time if we were to have an anomaly or abnormal condition on the spacecraft. And this set of commands for this flyby took up 80% of the total memory. So what that meant was that we had we had to clear 80% of that memory before we could actually load that set of commands on board the spacecraft. So we had the set of commands prior to that only could take up 20%. Then we'd have the 80% of the flyby, and then 20% at the end, and then we could do that seamless transition. So the encounter period, that 9-day period, was July 7th through the 16th, and the closest approach day was on July 14th. So the very first opportunity we had to load this set of commands to the spacecraft memory was on July 4th, because that's the point when that 80% of the memory became free and we could load it up. I'm just giving you the round trip and the one-way light times here so you can just see. So about 4:30 in the morning, we started sending the commands to the spacecraft. It took about 2 hours to radiate those commands. We were radiating at 2,000 bits per second. And a round trip time later, we were in the Mission Operations Center. There's about 5 of us watching the computer on board the spacecraft receive those commands. It was about 1 in the afternoon, and everything was going perfectly fine. At 1:55, we lost all communication with the spacecraft. And if you've been in an ops center, you know, green is good, gray is not good. And then when you don't have carrier, that's really bad. And so that is actually what happened. And here we are only 3 days before this flyby is supposed to occur. We don't get a second chance. So we were fortunate that many of us had worked together for, you know, since the program was being developed. And we had gone through a number of abnormal conditions or anomalies before. We had our checklist that we had been, you know, revising as on those many years, an approach to Pluto. And so we started down our troubleshooting path. I was speaking with my autonomy engineer. That's the gentleman that coded the autonomous responses to any faults that might occur on the spacecraft. My deputy was talking to the gentleman that coded the main flight computer. And I asked the autonomy engineer, what could this be, you know, given what we were doing? Don't tell me all of the faults that could be occurring. He narrowed it down to 2. One was a main computer reset, which we had seen previously. And the other one was a switch to the redundant computer, which we had never seen in operation. And I was hoping that we were not in that situation. So I asked him how long it would take to have our autonomy system reconfigure for each one of those scenarios. And the one with the switch to the backup computer would only take on the order of 60 minutes. I looked at the wall clock and we were about 77 minutes without any communication with the spacecraft. So I directed my flight controllers to reconfigure the deep space network, or ask them to reconfigure the deep space network to acquire a signal if we were under those circumstances. And we did. We acquired that signal at about 3:11 p.m. on July 4th. We locked up. It was a wonderful feeling, but the spacecraft was in a safe mode and it was spinning. And that's what the autonomy system will do to save the spacecraft. We're spinning at 5 RPM and we're outputting telemetry at 10 bits a second, which is painfully slow, but we had found the spacecraft. The question was, you know, did we have enough time to determine what caused this problem and to get it back into an operational mode or a 3-axis mode where we could accomplish this flyby. And by 10:30 that evening, we had developed a plan. And what we did is we calculated how long our procedures would take to get to the spacecraft and execute, and then how many round-trip light time periods we had, and we had about 4 of them. So we developed our recovery plan based on 3 of those, because we left that 4th one for, you know, just in case we weren't correct and there was something else going on. So we've sent our first set of commands on the morning of July 5th, about 3 in the morning. And we kept we'd send a group of commands, we'd wait a round trip light time to make sure that the spacecraft reacted to those commands, serviced those commands like we wanted them to do, because the last thing we wanted to do was to send everything up and then find out that something wasn't right or it didn't react the way we thought it should. So on July 7th, the morning of July 7th, about 8 in the morning Eastern time, we saw that the spacecraft had transitioned into this 3-axis mode, or this mode where we can take pictures. And then about 4 hours later, we saw that the spacecraft had transitioned into this flyby sequence, and we went on to have a very successful encounter. So let's see, this is fast forward. Now we are at early on July 14th GMT day, down here in this corner, the right corner, or July 13th Eastern time. And we have our last contact with a Madrid station before we fly through the Pluto system and collect all this data. Our spacecraft cannot collect data and be in communication with Earth at the same time. We built that spacecraft to have no moving parts, and that's because there's less risk of something breaking when it doesn't move. And so in order to communicate with Earth, we have to actually, or to point to a scientific, to observe something scientifically, we have to actually take the spacecraft and point the whole thing using these thrusters. And so the last thing the scientists wanted to do was to turn that spacecraft towards Earth, take a break from their science, turn it towards Earth, and communicate with Earth. But we did get a little bit of time here, about 24 hours later, where they gave us 15 minutes, and we were able to turn that spacecraft and shoot 15 minutes worth of telemetry just to assess the health of the spacecraft. But here we are here on July 13th, we get our last image down of the Pluto system, and then we're gonna fly through here. It's 22 hours taking scientific observations. Closest approach is our aim point is this closest approach, 11:49:57. Then we go to do an occultation with Pluto. So that's when the spacecraft's going to pass behind Pluto. So you can see the shadow here. And we had 7 DSN antennas trained on Pluto a one-way light time earlier. We were sending up signals with slightly different offsets. And the idea here is that these signals would be received by the spacecraft. And then once the spacecraft passed behind the atmosphere and then the planet and then the atmosphere, those signals would be attenuated or non-existent in the case of, the solid body here. And so this would give us a good idea of the atmospheric depth and component of Pluto. And then likewise, we did the same thing with Charon just a little bit later. So the next video I'm going to show is just the spacecraft, and it is moving. It's sped up, so the 22 hours is sped up into 20 seconds. And you'll see in the corner, you'll see the instrument that's doing the observation and the target. So whether it be Pluto, Charon, or one of the small moons, Styx, Nix, Hydra, or Kerberos. And then you'll see the distance as well. So this one does not have any sound. So here you are. See, the instruments are lighting up here when they're active. And then you have the target here, and then the distance. And then here we're coming up on closest approach. And then we're going to turn and look back towards the sun. And then it's going to start over again. So that kind of gives you an idea of what the spacecraft was doing in those 22 hours. So here we are now. We've flown through this Pluto system, and now we are at, July 15th Eastern time, just a little bit before, July 15th UTC time, July 14th, a little before 9 p.m. Eastern time. And this was our quick check of the health of the spacecraft. Did it survive? Did it record? Did the recorders look like they captured the amount of data that we thought should be captured? We normally don't have very many people in the Mission Operations Center or the MOC, but this night was very special. We had all of our engineering team inside the Mission Operations Center, and the idea was to get that first bit of telemetry, have those subsystem engineers evaluate the health of their subsystem and report their status to me. We had in the room that is separated the Mission Ops Center with glass, we had our managers and NASA head people. And the idea was that we would assess the health of the spacecraft, and then we would invite our leaders into the room. So this video does have sound, and so you should be able to hear it. But let me know if you don't.
And lock on symbols.
So that's the first step in getting data.
Okay, copy that. We are in lock with telemetry with the spacecraft.
So you can see the Mission Ops Center is very full. Lots of photographers. We are not used to that.
See a lot of green numbers in that one, too.
Yeah. Green is good.
Yeah.
You gotta get that, man.
And this is the Kozякov Auditorium. It is piped live into the air as well as onto the web.
Okay. PI, Mom on Pluto 1. We have a healthy spacecraft. We've recorded data of the Pluto system, and we're outbound for Pluto.
Yeah. That's it.
This is our PI, Alan Stern. Okay, so how did we do? This Pluto closest approach time, if you wrote that down before, you'll realize that we actually did not hit the exact aim point with that we wanted to. We actually came in 88 seconds early, and we were about 26 miles off the aim point. And from 3 billion miles from Earth, that's pretty good. But I always like to say, if we didn't have that little hiccup on July 4th, we could have done better. But that being said, the information that we were getting from the spacecraft said we were within that error box, so we decided not to do a little timing tweak that would have brought it in closer together, or closer to that aim point time. So this is what we had, our best picture of Pluto before New Horizons, and this is what the spacecraft returned. So you can see quite a difference. This is a composite picture. It is taken by the Lori black and white camera, and then the Ralph spectrometer, and the colors are overlaid onto the black and white picture. But you can see this iconic heart now. This is a glacier field. And then you can see this kind of gunky stuff. This is what they believe to be tholins. These are just hydrocarbons. And anyway, a lot. So the next video is recaps the launch 2006 through Pluto and some of the major discoveries that were made. So I'm going to go ahead and play that for you now. Okay, so you can see that was quite a lot of things that we discovered on Pluto that were totally unexpected. I mean, those ice volcanoes, the deep canyons, the bladed terrain, it was just amazing. The atmosphere, which is, I think, my favorite picture, at least 12 layers of haze that we can see in the Pluto atmosphere. So pretty amazing, but New Horizons wasn't done yet. We actually found another target. I spoke about it a little bit in the beginning of the presentation. 2014 MU69, nicknamed Ultima Thule when we were flying by it in the late December of 2018, early January 2019, and then formally named Arrokoth in January of 2020. So this is the sort of a picture overview of the spacecraft now on this yellow line, and then the target here, Arrokoth. So just to give a little bit of a comparison, so distance-wise, that's 1 billion miles farther from Earth. The flyby distance, this one always makes me smile because Pluto, we were given the target of flying about 7,800 miles from the surface of Pluto. And we'd known about Pluto since 1930, so 85 years we had been tracing its orbital path, and we knew it very well. And Arrokoth was only discovered 5 years before we actually encountered it, and only 3 years after we had to develop a set of commands that would accomplish these observations and the flyby. And that's because we need to develop the commands ahead of time so that we can test them and verify them. But yet we were given the target of 2,200 1,500 miles. And so that was a pretty tough one to do. So travel time, 9.5 years for the primary mission, 13 for the extended mission to Arakoth. Here you can see the light time delay. And then the power, we've actually decreased in power here. So we had to do a lot more switching. But the one constant here, it is a flyby mission. So we only get one chance to get it right. So besides flying close to a Kuiper Belt object, we also were, part of the extended mission was to image other Kuiper Belt objects that were not as close to the spacecraft, but obviously closer than Earth would be. So these are just some of the few dozen that we have imaged in this first extended mission. So one of the things our scientists use to gain more information about the object Arakoth and any object is to do occultations. And so an occultation, for those of you who are not familiar with it, you can think of it as an eclipse. That's essentially what it is. So in the eclipse, you have our sun, you have the Earth, and then you have the moon that occults the sun. And depending on where you are in the Earth will determine how much of the sun you actually see. So if you're in that zone where there's going to be a total eclipse, the moon will appear to block all of the sun. And if you're one on those outer zones, maybe you see a partial eclipse. So this is sort of the same thing with an occultation. You have an occultation star, and then you have, in this case, Arakoth. And then you have this spot on Earth that you are. So the idea is to be at a spot, calculate the spot on the Earth that you need to be in order to see a total block of the occultation star by Arakoth. So the calculation was that there was going to be 3 opportunities visible from Earth where we could see Arakoth occult the star. First one was on June 3rd in 2017. Unfortunately, we didn't see anything. This one was in Senegal in Africa. And it turns out there was a slight error in the calculation. So you can imagine how tight and how accurate these calculations have to be, because the object is very small and it's so far away. So you have to be pretty precise. July 10th was another opportunity. This one happened to be, you had to be off the coast of New Zealand in order to see the occultation. And so NASA has a plane called Sophia, and the team got into the plane, told the pilots where they wanted to be at a certain time, and then they opened the telescope and did the observing. So it's only one telescope. And so they saw what they thought was a blink or an occult of the star, but with only one measurement, it was hard to understand if it was a fluke or it was something real. So the very last opportunity to get information on Arakoth, which we would then feed into the spacecraft observing arguments, was on July 17th. And this happened to be on the coast of Argentina. So Argentina in the southern hemisphere, July, it is winter, coastal areas, lots of fog, not so good, usually not so good for observing with telescope. And this area is very, very windy. So the team pulled out all the stops. This is the center point here, this little town here. Each one of these blue bubbles is where a telescope was set up. So you can see they pulled out all the stops. They had, I think there's 24 or 25 of these telescopes set up. The red line is the point where the calculation says the full occultation will be, and then the yellow lines are the the 1 sigma and then 2 sigma here with the blue, and then they just put extra ones out here just in case. And so here's the big picture view. So the next video I'll show is a video that was taken and put together of that observation night. And it is a little bit hard to hear in some spots because of the wind. And then sometimes they write. So, but anyway, here we go.
Tonight is the big event. There should be a star that blinks out, but who knows if it's actually going to happen.
So this third occultation feels really important because if we don't catch the object this time, we'll have a lot less information going into the encounter.
I want to just say thanks to everyone for the past few days of work and to some of you for the past few months of work. Let's go get the data tonight.
Well, we're about to start in 10 minutes. All right. This is it. This is our last opportunity to learn something about MU69 before New Horizons flies past. All right. Hammer time. Okay, within the next minute. And I will tell you if I see the star disappear. Oh, I saw it. No way. I saw it. I'm pretty sure I saw it. Holy cow. I actually saw it. Holy cow. No, I really did see it.
We saw it. Yeah, we saw it too. Did you see it? Did you see it? You saw it, right? That's it. We got it.
We as a team succeeded in getting not 1, not 2, but 5 different occultations. So we saw the star go out and come back as MU69 passed in front of the occultation star at 5 different locations.
I don't care what the weather is today. That's a great feeling. Here it is Tuesday. It's rainy, windy, cloudy, really nasty stuff for astronomy. And it doesn't matter. It's great. It can do whatever it wants as long as I can get out on my airplane back to Buenos Aires tonight. It could snow 10 feet tomorrow for all I care. But we got what we came for.
So you can see that they were very successful. So how did we do? This is just a recap of the occultation campaign. So here's the first set of observations that were taken in Africa, June 3rd. And so each one of these lines represents the star being visible. So you can see there's no breaks in these lines. So that means the occultation star was visible the whole time. And then we have this observation here that was done with Sophia in the plane, 1 telescope. So they thought they saw a little bit of a break in the star. And so that's represented right here. But again, since we only had 1, it's hard to corroborate this observation. And then here we are with Argentina, they pull out all the stops, and you can see all these stars here, and then you can see the location of the telescopes that actually saw the occultation and the relationship of that break. And so I think, just find this fascinating because you have these, I know telescope observing is not low tech, but basically you're looking at an object 4 billion miles from Earth with a telescope, and you're just timing the amount of time that that star is not visible, and you can see a shape emerge here. Now, we don't exactly know what the shape is because we don't know what part of the rotation we actually captured this observation, so this just represents a point in time. And so some of the ideas of what the scientists thought they might be seeing based on this occultation data, these are, this is a binary, a contact binary, they're calling this the potato. So binary, so looking at it from this point of view, but you look at it from a different point of view and it could have this separation. So that's what these are supposed to do. And they're supposed to give us, some kind of idea of what we might expect to see. So fast forward to 2 days prior to closest approach. Remember, closest approach of Arakoth is on January 1st, just a little bit after midnight Eastern time. And here we are, December 30th, and finally we are getting pictures of Arakoth that are more than just 1 or 2 pixels, because that's all we've been able to see up to this point. We've been taking optical navigation measurements as we come in to make sure that we are on target for this Arakoth encounter, but we're only seeing little teeny bright spots of light, and we're targeting. We're doing correction maneuvers to target based on the information that the optical navigation data is coming back. So here we are, we see this on December 30th. This is the raw image, and then processed image is here. So, kind of looks like, people say, looks like a blob or a peanut. And then here we are 24 hours out, and now you can see it's starting to have some kind of shape. And now we're refining the length and the long direction, 21 miles. And then finally, now we have encountered closest approach, and this is what our LORRI camera sees on January 1st. So it looks quite different from that kind of blobby picture. When I first saw this, I thought it looked like BB-8. Some people thought it looked like a snowman. And then when we look at it with a little bit higher resolution, they're defining this as a contact binary, and this part is called the neck. And then one of the things that we did at Pluto is we looked back at Pluto after we flew by, and that was that picture that you could see the planet and then this blue haze or atmosphere around it. So we did the same thing at Arakoth, and we expected to see something different than we actually saw. So this is what came down. And this was unexpected because when you look at those pictures of Arakoth that are returned, it looks like it's going to be kind of round, or have a round shape, two round balls kind of stuck together. But this tells you that that's not the case, that they're actually flat. And that's because of the amount of reflection that we see here from the sun. And so we believe this is what it actually looks like. So it is quite unusual, sort of a pancake stuck to a walnut. That's what some people are calling it. And then how did we do with the occultation data that was collected? So here, they think that this one was a real detection, and that we were looking at it either head on or the back end. I guess it was the back end on. And then this fits pretty perfectly in this occultation measurement, which is amazing to me. And so this is one of our higher resolution pictures, and these objects in the Kuiper Belt are believed to be the primordial remnants of the formation of our solar system. So we can think of New Horizons as looking back in time to the period of when our solar system was being built. And so what are we doing next, and where is New Horizons going? Many times I get the question about where it is in relation to the Voyagers. The Voyager missions are still operating. So here you can see that New Horizons is sort of in the direction of Voyager 2. It is not as deep into the ecliptic as Voyager 2 is, but sort of in that same direction. And then the Pioneer instruments, spacecraft, they are no longer operational, but this is the direction they went out from space, from the solar system. New Horizons is continuing to take observational data. In fact, we are going to be in a 3-axis mode in May, and we will be taking some images of some Kuiper Belt objects that our scientists actually discovered with the Subaru telescope, that's in Hawaii. And once they discover them with the Subaru telescope, then they observe them with the Hubble Space Telescope to refine the orbital parameters. And then we load those onto the spacecraft and do observations. We are still looking for another flyby target. We do have enough propellant in the tanks to do probably one more, but it will have to be on the, not too far off the path that we were going out. So this are some pictures of the teams that I work with. It really does take a team to do something like this. Not a big team, but a team that has expertise. And so these are just a few pictures of focusing mostly on the operations and the engineering team. And then this one picture here in the Kazi Auditorium when we confirmed that the spacecraft was healthy after the flyby of the Pluto system. And then on December 31st, 2018, just before our flyby of Arrokoth, this gentleman visited the Mission Operations Center. He's actually a member of our science team. He's an astrophysicist. And some of you may also recognize him as the lead guitarist on Queen. So in this picture, he's actually showing me how to take a selfie. And I think that's it. If you want to see more pictures, videos, you can go to this website. There's also part of the website that's devoted to education. So there's lessons there for teachers, and there's things for kids as well. So thank you guys very much for having me. I'm more than happy to answer any questions that you might have.
Yeah, thank you, Alice. That was a excellent presentation. If there's any questions, please feel free to use the question and answer text area that's available in Zoom. We'll pause for a minute just to see if anybody has any questions they want to bring up. I actually have a personal one I'd like to explore, and that is when you perform the occultation experiment in Argentina. So that curve, that binary shape, that's actually what you achieved before the mission, and then you overlay to look like one of your higher resolution photos on it. That's how close, from a qualitative standpoint, that occultation experiment was.
Yes, and that is just totally amazing to me.
Yeah, I was fascinated. I remember reading about that when the experiment was ongoing, and I thought that was an interesting technique.
Yeah. So I agree. Yeah, and I think that has been used perhaps on other indirect observations of objects that are far away, but definitely that was a challenge because of this object being so small, on the order of 21 miles in the long direction and maybe about 9 in the narrow direction, and being so far from Earth. Yeah, and an occultation that lasted on the order of 5 seconds or something like that.
So, and the continuing mission, as it travels further and further outside of the solar system, what's the long-term plan for the mission when it's either no longer funded or the power levels are too low? Is it similar to the Voyager series where they turn off certain experiments and over time they get down to only a select few, or do you have any comments on that?
Yeah, sure. We believe that we'll be able to return scientific data until the mid-2030s. We will have to do some power switching. Our imagers, the Ralph Laurie and Alice instruments, are mostly used just in this 3-axis mode or stabilized mode. At some point, we won't have enough propellant to actually do a flyby where we would go into a 3-axis mode. And so we believe what will happen is that the particle instruments will continue taking data, so that SWAP, Pepsi, and SDC. And those together, they take less than 10 watts. The transmitter is obviously the most power hungry thing we have on board. It's about 32 watts of power. So mid-2030s is where we think we'll reach that point where we won't be able to return scientific data because of our power levels. But our mission system engineer is doing some work trying to figure out what we can actually turn off to extend that a bit. And it also depends on that radioactive decay, how that curve is going. So each one of these RTGs has a little bit different of a curve. So you can sort of estimate where you think it's going to be, but you really won't know because of your particular RTG.
Yeah, understood. There was actually a good question that's related to this topic. How far or how long until you're past the Kuiper belt, or do we understand if we'll be able to get to that point while we still have power to transmit back?
Yeah, that's an excellent question. 50 AU is where, prior to New Horizons, they thought that the Kuiper belt ended. So it starts right around where Neptune's orbit is. Like maybe, I think that's about, I don't know, I can't quite remember, 30 or so, maybe a little 25, and then goes out about 50 AU. Obviously, at this point in the mission, we are going to be 50 AU, and that's measured from the sun to the spacecraft this month. And we definitely are seeing a decrease in the Kuiper belt objects that we're detecting. But there is some thought that perhaps that you have a Kuiper belt that goes out to 50, and then you might have another set that maybe starts a little bit later, and then we're going to go through that a little bit later on. So I can't speak to what gives our scientists reason to think that, but I know that that's something that they are looking at.
Fascinating. Well, I don't want to keep our meeting running too long. If there's any other pressing questions, feel free to email to the Hampton Roads section after the fact. We will be posting this video to the Engage website and send that link out to everyone within the section. But I'd like to thank you sincerely for your time giving us this presentation. I found it fascinating, and I'm sure the other attendees and the people who will watch it later on enjoyed it as well.
Oh, you're very much welcome. Thank you so much.
Thank you. All right, everyone have a good evening.